Okay, everyone, welcome back. This will be the last of the 3 exams that pertain to the final exam review for electricity and magnetism. Again, the entire exam, the entire practice exam for electricity and magnetism, all 72 problems will scroll at the end of each one of these 3 films, parts 1, 2, and 3. In addition to that, in addition to the entire exam, 72 problems scrolling at the end of each one of these films, all the solutions, all 72 solutions, in a relatively detailed manner having been solved, will also be scrolling. All 72 solutions will scroll at the end of each one of these 3 parts. In totality, we're only doing on film half of those problems, 36 problems. But all 72 problems are going to be on each one of the films, and people can look at them there and work with them. And those in my class, any of my classes, we can also go into more detail as well. But this gives us some sort of a flavor of what we're trying to do. It just seems to be the most time-efficient way to do this, to say, okay, let's have the PDF solutions available in many different formats. For those that have me as a teacher, you have it on the Canvas format. You have the entire practice exam there. You have the entire practice final exam there, and you have all the solutions from that entire practice exam, practice final exam. You have all those solutions entirely present for you in Canvas, all 72 solutions. You will also have that at the end of each one of these films. Again, and we're going just a little more, from the film aspect, we're going to do half of them in total. Hope that'll be of use to you. We split them up into 3 films. We think that's a little more, I've been advised it's a little easier to digest something like this when you spread it out over 3 films. This will be the last of the 3 films. It's all there for you guys. The PDF documents are there as well, and all those documents in their entirety. All 72 problems are scrolling at the end of each chapter. So you've got a pretty good deal there. Anything is, of the 72 problems, anything is fair game on the final exam. Anything of the 72 problems. It's not just the 36 that I'm putting on film and solving them explicitly on film. Everything that's been solved for you, all 72 problems, and they are readily accessible to you, because they're readily accessible to you, they are all fair game on a final exam. But it's not too bad. I mean, the problems themselves, with a little bit of effort, you get through all 72 of those problems, and you're in really good shape to do well. Again, doing them on film a little bit gives us a little bit of an in-person flavor to what's going on. Sometimes there just isn't the time to do as many problems as we can do on film sometimes. Okay. All right. We will talk soon, and we will get to part 3 very shortly. Thank you. Hello, everyone, again. Let's look at the last of the 3 parts of the practice final exam for electricity and magnetism. Again, there's 72 problems total. Those problems, those questions will be scrolling at the end of each one of these 3 videos, parts 1, 2, and 3. Each time you'll see all 72 problems scrolling at the very end, and all of the detailed solutions for those 72 problems will scroll at the very end of each one of those videos. Parts 1, parts 2, parts 3. Absolutely. I will solve more or less in person, if you can call doing something on film in person, I guess you could say. I will solve half of those problems, 36 of them, randomly selected for practice, a little more enrichment on it. But all 72 problems are fully solved for you. And if you're in one of my classes, you have full access to those and easily can get a hard copy. If you're not, if you're not in one of my classes, you still have these scrolling at the very end. Okay? So that is where we are regarding this, guys. I might have to cut away just a little bit and get my glasses. I don't have them with me, but right now let's work with what we have. Let's look at problems to finish this thing out. Let's look at problems 56, 57, 58 to take this thing all the way down to the end. Okay, so let me just step away for one brief second here. Let me put this up here. Just so we're in agreement here what's going on. Here's part 3 to finish this whole thing out, you guys, that we're going to be doing. And let's see here. Let's look at problem number 56 and kind of take it from there. Let me step away for just a little bit of time so I can make sure I can have some of the stuff that we need. But without my glasses, I should be able to read some of this stuff right now. This is a 12-volt battery. We're going to pretend all the current flows from the positive all the way around back to the negative. It's going to be a positive flow of current, and there's going to be some questions that they're going to ask you regarding this. I don't think anybody's going to mistake me for being an artist, guys. Let's see what we got here. Two ohms, 4 ohms, 6 ohms, 10 ohms. Six ohms, 10 ohms is the setup here. And let's see what's going on here. Let me just pause this for 1 second so I can get some glasses here, guys, really quickly, and we'll take it from there. Okay, folks, back we are. Got some of the glasses that I needed on this one. So what we're doing is, for number 56, they're asking the question, there are 3 resistors connected in parallel via individual, or forgive me, for number 56, there are 3 resistors connected in parallel. The 3 resistors connected in parallel have individual values of 4, 6, and 10 ohms, respectively. If this combination is connected in series with a 12-volt battery and a 2-ohm resistor, what is the current in the 10-ohm resistor? Pretty straightforward stuff in that regard. Number of ways to go here, I guess you could say. We can look at it and say, okay, I'll tell you what we're going to do. We will say that let's find out some things that are going to help us out. The total amount of current going into all of this situation and the total amount of current coming out is going to be the equivalent resistance divided into the potential difference that's initially present. In plain English, E divided by R equivalent will get you the total current coming in, and from there we can kind of draw some conclusions. Well, interesting in its own right. I mean, there's a lot you can say here, guys. We will say, let me just see exactly how we want to do this. You can call the current coming out of here and the current coming into here before anything goes on. You can call it I, or you can call it I1. I think I'm just going to try to be consistent with what I've written on there. It's I1. When it actually, let's have a look here. That's that. And that's also going to go through this guy as well. That I1 is going to go through here. Then it's going to separate 3 different places, and it's going to be I2, I3, I4. Sounds good to me. Going can look at a bunch of stuff here. Let's see exactly, let me see what kind of order I want to take this whole thing in. We're looking at this happening here. Now again, guys, when you're doing the real life exams, and again, the final exam that I would give for classes that I teach, any one of those 72 problems is fair game. Because we're going to talk about them in person if you're in my class. Any one of them that you want to talk about, whether I've discussed it or not already in person, you can talk to myself or to anybody else about any one of those 72 problems. So any one of those 72 problems is fair game. In addition to that, it's about as simple as that. Anything is fair game. So because they're fully solved in a comprehensive manner, hopefully very clearly for you. If something's not clear, you talk to me and we resolve it. It's not going to be an issue. But any one of those 72 problems is fair game. They're scrolling at the end of each one of these 3 videos, parts 1, 2, and 3. At the end of each one of these films, parts 1, 2, and 3. With that in mind, I mean, you don't have to deliver a speech to anybody, nor to yourself for that matter, I guess you could say, when you're trying to solve these problems. You get through them fast. You're not running across 30 feet of a room trying to make sense of this and then try to explain it to somebody else. You're explaining it to yourself, and there's ways you can shorten this up. I don't want to shorten this up too much because I'm trying to explain how to do some of this stuff, okay? So there's reasons for everything, I guess you could say. When you look at it, again, this is the I1 or the I. I called it I said I equals I1. And you got something looking like this, like this, like this. So it could be this, how they all add up. When you look at it, you know a bunch of things. You can say a number of things, actually. You're going to say what I equals I1 is going to equal. Let's not cross that bridge just yet. Let's find out what that is, but let's have it in our mind and eventually get it done. We do know, at least somewhere here, that I, which is equal to I1, is the sum of all of these branching out from it, and then it comes back in as I equals I1 right here. So it's equal, each one of these is equal. Each one of them, they're not equal, but the sum of these 3, I2, I3, I4, is going to equal I, or I1. So you got I2 plus I3 plus I4. Okay, pretty important stuff in that regard. We've got this in our mind, and we're going to draw some more conclusions about it as well. We can say a lot of stuff. Maybe you can, yeah, there's a number of ways you can go here. There is a situation where, okay, if this is I2 and it's got 4 ohms, and this is I3 and it's got 6 ohms associated with it. So I2's got 4 ohms associated with it, I3 has 6 ohms associated with it, I4 has 10 ohms associated with it. The greater the resistance, the less the current, proportionally speaking. Let's call this guy the I2. Let's just call it I2. So we can go up here, kind of putting the carriage in front of the horse on this one, but let's start with I2 being whatever I2 is. Well, let's talk about that. If this is I2 coming down here, it's a bigger amount of current than I3 because 6 ohms is, what's the ratio of 6 divided by 4? Good way to look at it. What's the ratio of 6 divided by 4? It's 3 halves. This is 3 halves times, this is 3 halves or 1.5 times the resistance, which means it's 1.5 times smaller. It's 3 halves times smaller current. So if it's 3 halves times smaller current, you can say a lot. You can say, okay, well, I2, it's 3 halves times smaller current, which means that, it's a number of ways to go here, I guess. I just want to make sure everybody's going to come with me on this. This is 4 ohms, this is 6 ohms. Because this is a greater resistance, there's going to be less current proportionally speaking. 6 divided by 4 is 1.5. It's going to be 1.5 times smaller than this. So the I3 is going to be 1.5 times smaller than this, which is this, which is this. A bit convoluted, but there it is. So the I3 that we got here is going to be 2/3 what I2 is. My friends, essentially we're playing the same game over here. 10 ohms is going to have the smallest of all the amount of current going through this particular branch. Why? Because 10 ohms is substantially bigger than 4 ohms. How many times bigger is it? Well, what's 10 divided by 4? 10 over 4 is 5 over 2 is 2.5. I3, was that I4 rather, I'm sorry. I4 is 2.5 times smaller than I2. Do the mathematics, you get to here. So that's 2/5 what I2 is. Notice we made I2 the real big thing that's going to make everything what's going on here. So what we're saying here, guys, we made them. You got to have measuring sticks in mathematics. You've got to have something to compare to something else in a very logical manner. In a very logical manner, you have to have comparison. You have to have a good comparison of what's happening here. I think we got it. We've got, I3 is that in terms of I2. I4 is that in compared to the same one. You got to have something common there to make this thing work out. So what you're doing is, at the end of all this, you kind of just have it in the back of your mind what's happening. Now, are we going to need all this? You can perhaps argue that a number of ways. Oftentimes, to solve for one quantity for which you want to solve for that one quantity, you need to solve another other one. So, there's nothing wrong with knowing a lot, guys. Nothing wrong with being able to solve a lot of this. So we got what we got. We have a situation where I equals I1, whatever that's going to be, right? We've got a situation where I2 equals I2, whatever that's going to be. We've got a situation where I3 is going to equal 2/3 I2. And we've got a situation where I4 is going to equal 2/5 I2. Notice how we're using I2 as the measuring stick. Even here, the I1 being equal to I, we got I2, which is 1 I2. We've got 2/3 I2. And we got 2/5 I2. So I guess we chose you can choose any one of these three. I2, you can choose any one of these three, I2, I3, I4, as your measuring stick. That's not an issue. So that's the I1, same as I drew it over there, and you got all of this going on, and that pertains to all this. So essentially we have 4 unknowns, but we have 4 equations and 4 unknowns. So, well, yeah, absolutely. 3 unknowns here, you put them together and you get the 4th unknown. Not too bad, not too bad. So we got this, okay? Somebody could say to me, okay, so what do you want to say? Well, I'll tell you what I want to say. I mean, let's find out what the big I is. And then from there, it's just a done deal. We know, let's take a look at these 3 parallel items, 1, 2, 3, which are actually associated with I sub 2, I sub 3, I sub 4. 4 ohms, 6 ohms, 10 ohms. The equivalent associated with the parallel is 1 over 2 plus 1 over 6 plus 1 over 10. Sounds good to me. Plays out a lot of ways, guys. I guess you can do a lot of things here. You go for 30. I'll tell you what, you do a special one here, 15 over 15, and I got 15 over 30. Let me do a special one, 5 over 5, and I got 5 over 30. Let me do a special one called 3 over 3, and I get 3 over 30 equals 1 over RP. There's a lot of ways to go here. You might want to just do this with a calculator, get a final decimal answer, and get the reciprocal and get R sub P. That may be the fastest. That may be faster. I'm kind of doing it, I guess you could say like an old math teacher. I'm trying to show maybe a different sense of rigor here, perhaps. I don't know. In the end, it's up to you guys. You're not delivering a speech here running all over a room. You got to get this thing right. It's about as simple as that. You add these together, you got 23 over 30. If these two are equal and they're both non-zero, being equal to each other, then R sub P, if two things are equal, their reciprocals are equal. If there's no zeros involved here in any kind of division, we got it down to here. That's in ohms. Okay? The one R sub S, the R equivalent is going to be an R sub S plus the R sub P. The R equivalent is going to be 2 ohms. That's that. That's the one initially, everything's going out, and you got 30 over 23. Okay, guys. Okay, for some reason, I am almost not agreeing with this. Just make sure. Is there a 4 in here? Yeah, okay, there's a reason I'm not agreeing with it. There's a 4, a 6, a 10. Okay, that makes perfect sense. All right, let's try it again. It's the same argument. Hopefully everyone does the right mathematics, as I failed to do this time. That is a 4. Forgive me. At least the notes are right. So far the notes have been spot on, you guys. Though I've not been spot on. I was spot on with the notes, but sometimes in person I'm going to make some mistakes here. 1 over R sub P is equal to, okay, let's just try it one more time. Let's go for 60 down on the bottom. 60 on the bottom, 60 on the bottom, 60 on the bottom. Let's see what we can do here. 15 over 15. 15 times 4 is 60, 15 right here. 10 over 10. That gives you the 60, 10 on top. 6 over 6. Now we go, that is something over 60. 15 and 10 is 25, and 6 is 31. Okay, that explains it. Okay, there it is. REQ. If two things are equal, their reciprocals are equal. Okay? This is actually inverse ohms. I don't like writing units. If I already know where the units are going to go, if I'm very confident where the units are going to go finally, there's no need to write too much. As long as you know the units are on the mark at the very end of things, don't worry about it. 1 over RP equals 31 over 6. So RS is the 2 ohms. That's way, way over there. That's the one I used erroneously for the other thing, but that's way over there to the far left. On top, that's 2 ohms. That's associated with R sub S. And the reciprocal here is 60 over 31, almost another 2. It's going to add up. The equivalent is going to be equivalent close to 4, not quite. A lot you could say here, I guess you could say. That's going to be 3 and 29 31st. It's pretty close to a whole 1, isn't it? Whatever. We got our answers here. We got this. Let's see what we can say here, guys. 2. Let's see what we have here. 2 is, a special 1 here would be 31 over 31, 62 over 31. 62 over 31 added with 60 is 122 over 31. Yeah, looks pretty good to me, ohms-wise. Now, maybe that's going to make some sense. There's a lot of ways you can write this, guys, and a lot of things I'll let go when we're doing it. The real big thing that's going to get us here, 121 over 31, this final song and dance right here, let's nail it with some numbers here, and we'll kind of take it from there. The R sub EQ is 3.9355. R sub EQ is 3.93. That's a big move. I mean, if we get to here, it's pretty clear sailing, guys. You come back to here, and they're telling you that I is equal to the E, which is 12, divided by the EQ. The EQ is pretty close to 4. The answer should be pretty close itself to 3 amps, a little bit more than 3 amps. So let's see, we got 3.9355. Okay, I mean, we talked about it. I think we talked about it. I think we're strong. I mean, so we get down to here, we end up getting the big one, everything coming in and everything leaving immediately before it gets to here, and even when it does get to here. In fact, when it gets to all, forgive me, when it gets to all of these, actually, it'll come into here and it'll go out there. What goes in goes out. We're talking about 3.05 amps. Well, nobody asked you this question, but if they did, you can answer it. And we just did it. They didn't ask us a lot of stuff. I think we need to answer a lot of stuff, honestly, before we actually get an answer anyway. But, I mean, that's its own dynamic. But we got this. So, excuse me, guys, I just lost my mic here. Make sure it's still functioning. Okay, yeah, it's functioning. We're doing good. Okay. So far, so good, yeah. It's going okay. All right. Try to make this thing a little bit more resilient for what I'm doing. Okay, this might be a little bit better. Okay, so we have this right here, guys. You're getting the total current. I mean, there's a lot they could ask you here. There's any one of about 5 or 6 different questions they could ask, theoretically, in a question like this, which is kind of neat in its own right, and we know how to do it. We can kill a whole bunch of birds with one stone, basically, when we're doing this stuff. So what we're doing is, okay, so let's see what we got here, guys. The rest should be pretty straightforward stuff, you guys. What we can do is, we've got the I sub 1, we got all these. Wow, we can do a lot. I mean, we can look at this and say, okay, well, what are you talking about? Put some a little on the side here. We got all this. We've got this guy, 3.05 amps. Let me see if that's legible, you guys. I'm using the green chalk trying to differentiate it. Doesn't do me any good if you can't read it. I'm going to go with the white chalk, actually, on that one, and then I'll just put the green around it. 3.05 3.05 amps. We know it's amps, so I'm not even going to put that in there. I'm going to put it like this, maybe make it a little less cluttered. And yeah, let's go for it. Let's get I sub 2. Let's get a whole bunch of stuff and then get the other ones. I got 1 I sub 2 plus 2/3 I sub 2 plus 2/5 I sub 2. That's a lot there. I can do a whole bunch of stuff here, guys. I could stay with the fractions or get off the fractions here. This is 0.67. This is 0.4. You add 0.67 and 0.4, you get 1.07 plus 1, you get 2.07 or 67. You know, the 6's go forever, I sub 2. Divide by 2.067 on each side, you get I sub 2. And let me just make sure we're agreeing. Again, the notes might be a little off. Depends what kind of precision we're talking about when we're doing this. 3.05 divided by 2.067. Make sure I'm doing this right. I don't want to do anything careless here. I'm getting 1.4755, 1.4756. Okay, so I kind of went here, and I want to make sure I did not make any careless mistakes. Anybody can make them. I make my share more than enough times. But I'm getting this for an answer for the I sub 2. And then from there, you're talking about, let me see exactly. Let me just kind of make sure we're all agreeing here. For some reason, right. 1.4754, it's saying here, 754. I don't know where I got the 7.5. That's not it. We're not going to nickel and dime this to the 10,000ths place. I got 1.4754. I think it is going to be, gee, that's weird. Where the round off was. Maybe the round off was here, where I put 2.07. Yeah, I might have put 2.07 right here, and that's going to give it a little bit of a smaller answer. That's not a big deal, guys. We're not going to nickel and dime 10,000ths place. Okay, let me just kind of agree with my notes, but either one of these is fine. Nobody's going to create an issue for you. As you're doing this, okay, you got to here. That's the I sub 2. So there's your I sub 2. The I sub 3 is going to be 2/3 of that. So the 2/3 of that I got 0.9886. Again, they're getting a little bit different numbers here, not too bad. Again, I don't know where the round-offs went, guys. Where you're going to get different answers when you do this. 0.9886 is what I got. In the notes here, I got 0.9836. I'm not incredibly, I don't like that a lot, but it's at the thousands place, so no big deal. Essentially, guys, that's kind of the answer here. Now, the way I was doing it, I think I probably stayed with the fractions. I mean, flat out with the fractions, and that really probably got a little bit level of precision that was more than the other one. But you're getting on this one 0.9836. Uh, 0.9836 on that one. And the other one, again, we can do, I don't know, maybe perhaps is a better way to do it. Let's go with the logic that I initially had. If we're going to call I2 1.4754, and we're going to divide by 3, then multiply by 2, 0.9836, that's where I'm getting the 0.88. So I'm using when I did this, guys, I flat out used the fractions. I didn't go for decimals. You ain't going to be that far off if you use the decimals, but there is going to be the chance that things go off a little bit. To the hundredths place, you should be fine. Mostly to the thousandths place, you should be fine, but there could be some disparity. Got to remember, a lot of times when you're doing this, you're doing a calculator answer, and you're really letting the decimal expansion go a lot further out. So there shouldn't be even the disparity that I got. Not that there was a big disparity, guys. So this is good. I'm going more with the I'm literally going 2/3. I'm literally going for I3, 2/3 of the answer I got here. And the answer I got here was vis-a-vis not this division, but this thing right here going further out, which well, I don't know, whatever. The answer should, this is the procedure, guys. You should get in the ballpark. You shouldn't be too far off when you're doing this stuff. Again, the best precision is probably staying with the fractions. If you go with the decimals, go really far out. The other one, again, obviously this one's kind of doing some interesting stuff here. So you're doing here 1.4754, 1.4754. We're saying 2/5. I'm going to multiply by 2 and then divide by 5. I'm really dealing with the fractions here. I'm getting 0.59016, and that's what's going on here. 0.59016 as well to get all of this. So you're getting a lot of stuff here, guys. You're getting, go about this what you feel is appropriate. If you're going to be using flat out decimals, probably go really far out, maybe even farther out than I was going, and you should get these numbers. I prefer to use fractions. Right here, if you'd have kept the fraction right here, you're probably getting a different I. Certainly not by much. Everything should be in the ballpark, but nonetheless, you could get something different. This is 3.05 amps. I sub 2. And again, I played it pretty, like I said, I played it with fractions. We're going to do it. I sub 2, we said, was 0.9836 amps. And I sub 3, forgive me, correct, I sub 2, right. I sub 3, we said, forgive me, that was I1. I2, we played a number of games here, and once again, right, whatever answer you get here, guys, for I2 is indeed going to be this. Okay, I'm sorry. It's going to be that. 1.4754 I sub 3 is 0.9836 amps. I sub 4 is 2/5 of I sub 2. So 1.4754 times 2/5. times 2/5, which is just 0.4, and that's 0.59016. Correct, 0.59016. That's everybody. Okay, I mean, that's good. That's good that it's everybody. Again, a lot of ways to go. I guess the one with the most precision, the one with the greatest accuracy of an answer that you can get, typically is working with fractions all the way through. That's not always very convenient. You don't necessarily have to do it, even. But take the decimals, if you're going to convert the fractions to decimals, take them pretty far out. Even when I'd taken them pretty far out, I was getting some kind of disparity. How much of a disparity? Well, it can't be that much. It can't be, there is some disparity sometimes, but it's got to be in the ballpark. Well, what's I4? I4 goes through the 10 ohm resistor. I3 goes through the 6 ohm resistor. I2 goes through the 4 ohm resistor. And I is, in total, what's coming in, what's coming out. That I, which is equal to I1, also goes through the 2 ohm resistor. All of it, way up there to your far right, the 3.05 amps is going, 3.05 amps is going through this. For I2, 1.4754 amps for I2 going through the 4 ohm resistor. For I3 going through the 6 ohm resistor, it's 0.9836 amps. And for I4 going through the 10 ohm resistor, it's 0.59016 amps. And that is the question. That was kind of the question on this one, guys. They're saying what goes, I mean, we answered a lot of things. Sometimes I think you're forced to do it. I don't know that there's a way you could have done this without answering everything, even stuff that you're not being technically asked. Here we answered everything. We know what we need to know. I4 is what's going on. It's 0.59016. And I think the key is wrong on this one. I'll tell you what. Let's play devil's advocate on this whole thing, I guess you could say, in some sense. What is the current in the 10 ohm resistor? They gave an answer of A, that's 0.55 amps. What is the current in the 10 ohm resistor? What is the current in the 10 ohm resistor? They're saying 0.55 amps. I wrote here, their key is likely wrong. Go with what I wrote here. I tell you what, let's play the devil's advocate on this thing, guys. They're giving A as an answer. They're giving A as an answer, and that's fine. And if they're giving A as an answer, we'll take it. They're saying 0.55 amps. The answers they got here, I do not like going this direction. They got A, B, C. They got A, B, C, D. A is 0.55 amps, B is 1.0 amps, C is 11 amps, D is 16 amps. 11 amps and 16 amps are out of control. 1 amp or 0.55 amps. 0.55 amps is a heck of a lot closer to 0.55 is really close to this. If you really got your hands tied, go with 0.55. It's kind of sort of close to this. It's off by 0.04. I have no idea how they got that answer. They must have been doing round-offs all over the place, and we already talked about that. That can happen. So as far as like more rigorous way to look at it, their key is likely wrong in terms of great rigor on this whole thing. Go with what I wrote here. The answer keys that I've consulted to get some of this stuff under control, they're great. They do great work, and I would have a very difficult time doing a lot of things if it wasn't for being able to consult manuals and keys and other people's great work. On occasion, I'm going to catch people doing mistakes. They catch me doing mistakes all the time, and I'm basically corrected by looking at their great work. Sometimes I'm going to catch them doing a mistake. I think they made a mistake here. Or they were just doing a lot of round-offs, and maybe that would account for it as well. So not necessarily a bad thing on their part, but that's just something to keep in mind. That's number 56. Let's look at 57. Let's have a look. Right. Let's look at 57, guys. Let me clear out some stuff here and take it from there. Let me pause this real quick. We'll be back in an instant, actually. You'll see that on the thing, but I'd like to have this cleaned up a little bit. Okay, guys, we're looking pretty good. Let's go to 57. Okay, folks, let's continue. Make sure I stepped out a little bit. Wanted to just try to set this up, and let's talk about number 57. Let's make sure we're on here, guys. Okay. All right, sounds good. For number 57, they're saying, what is the current through the 2 ohm resistor? They basically want to know what the current is through the 2 ohm resistor. Well, forgive me. Yeah, right, exactly. What is the current through the 2 ohm resistor? Well, we know a bunch of things, guys. If I'm going to draw this out, I'm going to make I guess you can say the drawing and say, look, from the 8-volt battery, there's a current I1. From the 9-volt battery, there's a current I2. They both meet up here, and what exits is the sum of I1 and I2. We'll call that I3. I3 comes up here, and then it splits again and goes to what was going on over here. It goes to I2, and then goes to I3. Forgive me. Goes to I1, rather. Goes to I2 right here, and then goes to I1 over there. So I1 and I2 together become I1 plus I2. We'll call it I3. I3 comes up here and it breaks up again into I1 up here and I2 over here. All right, guys, from here we can use Kirchhoff's rules and determine a few things. We know a good amount. Let's keep that in mind. We know, whatever we need, we'll use whatever we need. It doesn't hurt to know something. And we can always confirm certain things. But let me say this. We know this is true. I've got 3 unknowns, my friends. I got I1, I2, and I3 that are unknowns. I have 3 unknowns. I need 3 equations for 3 unknowns. I need as many equations as I have unknowns. Well, I'll tell you what. Let's start with number 1 up here and say, okay, what's going on here? What happens here is you go this way. You go from here to here. That's plus 8. You go over here, that's minus 2I1. You come around here, you try to go the other way, I guess you could say. So let's see what I'm going to do exactly, guys, how we actually ended up doing that whole thing. We did not get that. Let me, right. We do that, then we go to the 6 right here. This is going in the wrong direction, so you're going to increase. So it's going to be 6 I2. We have to account for that with the potential drops or potential gains. So you're gaining, so it's plus 6 I2. You come through here, you're going through this thing, it's minus 9, and then by the time you come around here, there's nothing else. You already started over here, so there's nothing else going on. So for the first situation, the top loop, you're looking at, I wrote it like this, you're looking at 8 minus 2I1 plus hook around, you're going the wrong way, so you can actually, when you go through quote-unquote the wrong way, so you're actually going to gain something going through there, and then you're also going the wrong way through this thing, so it's coming out at you and giving you this, minus 9. And that's equal to 0. All right. We know this to be the case. We certainly already said this. I got 2 equations in 3 unknowns. I need 1 more equation. Though I should have numbered them 1, 2, 3. That one I didn't even number. I'm going to stay with my notes, guys, so make some kind of sense out of it. What do you want to do about this? Well, I'll tell you what I'm going to do. What I ended up doing is I solved for I2. And what happened was this. I forgive me, what did I solve for? Yeah, I solved for I2. Tell you what I'm going to do. I'm going to add a positive I1 on each side. I'm going to add a positive 2I1 on each side. I'm going to go 6 plus a negative 9, or forgive me, I'm going to go 8 minus 9, or 8 plus a negative 9 to get negative 1. I'm going to add a positive 1 on each side. I1 plus 1 to get to here. I'm going to divide by 6 on each side. I forget we got it on film here, guys, so I don't have to, I can erase some stuff and give myself room again. Divide by 6 on each side. Well, for better or worse, we get to here. Okay, not a bad thing to look at, I guess you could say. That all happened to get to here. Sounds good to me. So what we can say here is, from all this song and dance, from this right here, this first quote-unquote number 1 equation, the top has what it has. Maybe that should have been the number 1 equation. But let me stay consistent with what I did. This is what I get after this song and dance. Okay? Sounds good to me. So these are associated with one another. These two are associated with one another. Tell you what I'm going to do. Let us erase this a little bit and kind of go for the other one. And this stuff should go pretty, hopefully straightforward, guys. It takes a little longer. These problems are easier to do when you're not worried about explaining it to somebody else and running all over the place with it. They're still not easy. They're still not necessarily easy. You got to pay attention and you got to get the right answers. We know that. Something like 2 is going to look like this. Why don't we go down to this place right here and say, okay, how do you want to go here? Let's start here and deal with this loop. I'm going to start over here, gain 9, lose 6I2, come around here, and here's where I got the I3. The I3 is, here's where I got the I3. The I3 is I1 plus I2, so let's keep it. The I3 is equal to I1, so I can leave it as I3, or I can put immediately quantity I1 plus I2 going through here and losing there. Tell you what, let me stay consistent with my notes and try to make some sense out of it. You are going. You're making the move from here to here. You gain 9. You lose 6I2. You come around. You lose. Now this is neat. You lose I3. Now I3 is I'm already making the move. I3 is I1 plus I2. I'm going to make that move here so I can just stay with these two. You do all that, and that's it. All gains and losses are done at that point. You get down to here. And then that's this. So I guess you can have these two equations, but the only way you have these two equations is if you look at that third equation, which was the first one we put up there, and it would have been I3 times 4. It would have been 4 times I3. Well, I3 is already this. So you get what you get. What can we say here, guys? Let me try to think what we can say. So let me leave that there, and let me kind of see what I've done here, guys. I'm following my notes, but I'm trying to follow them in maybe a better manner than how I wrote them. The reason to talk about stuff like this sometimes is maybe it's easier to talk about it and easier for people to see it rather than always blindly looking at the notes. The notes should be okay, I think. That's my opinion on it. You look at this. 9 is 9. This is plus a negative 6I2. This is plus a negative 4 being distributed throughout, and you're getting this. And we got that. Negative 4I2 is this. Negative 6I2 is that. When you add those together, you get something pretty interesting. You got the 9 looking what it's looking like. Negative 6I2 and negative 4I2 is negative 10I2. So we've got minus 10I2 here. Negative 4I1. You can leave it in terms of the subtractions, you guys, and get to here. That's equal to 0. Well, again, with the help of that first equation among the 3, I was able to bring it down to 2 equations. I got it down to here. Now I can substitute 1 into 2. I mean, it's a little messy how this whole process, how to write this, how to write these, but we know how to do it. I'll tell you what, here, I got the 1 right here. I got the 2 right here. Hopefully that's legible, you guys. Maybe makes it more legible, I guess. Here's 1, here's 2. You got it. Substitute 1 into 2 and see what we can say. Wherever you got an I2, you can put that. Well, here's an I2, guys. 9 minus 4I1 minus 10I2. Here we go. 2I1 plus 1. 2I1 plus 1 over 6 equals 0. A lot of ways to go, guys. I prefer plus the opposite. Plus the opposite. I prefer addition if you're going to pull this thing off. At the end of the day, you got 9 plus 4I1. This times this. Well, this right here reduces to negative 5/3. A lot of ways to write this. This fraction, 10 over 6, is 5 over 3. Negative 5/3, that's negative 5 multiply across. Negative 5 multiply across. The thirds right here. I didn't get too odd about this whole thing. My notes, I do it a little bit differently, but we don't need to lose a tremendous amount of sleep on it. There's other ways you can pull this off. Once you get to here, multiply by 3 on each side. Multiply by 3 on each side. You got 27 plus 12I1. You multiply everything by 3 on the left-hand side. You multiply everything by 3 on the right-hand side, and you get negative 10I1 plus negative 5 equals 0. Okay, negative 5 and 27 is 22. 12I1 and negative 10I1 is 2I1. Make sure we're on the mark here, guys. We're doing this. Let's make sure we are there. Yeah, right. Here's this. This is a negative. This is a negative 4I1. So this is negative 12. I'm sorry, guys. That negative 4I1, multiplied by 3 on each side. Multiply by 3 on each side. This negative 4I1 becomes negative 12I1. This is this. This is that. This is that. This is that. Which means, again, just be careful. Careful. Negative 5 and 27 is 22. Negative 12 and negative 10. Negative 12I1 and negative 10I1 is negative 22I1. Equals 0. Add a positive 22I1 on each side. Add a positive 22I1 on each side. Divide by 22 on each side. Wow, it's a long Long path to get 1 amp there, but we got the 1 amp. That is I1. So it's pretty interesting in that regard. Let's just make sure we are okay. Right. I1 is 1 amp. So, I mean, there's a good amount we can say here, guys. I'll tell you what, let's kind of explore here. For number 57, the answer is 1 amp, and that's A. You're done. End of the problem. By the way, that's I1. What are the rest of them? Nobody asked you. Nobody asked you. But if he asked you, by the way, what's I2? What's I3, which is the sum of I1 and I2? What is that? What's going on here? How do you do this stuff? Well, okay. It's not bad. If I sub 1 is 1 amp, if this is 1 amp, we see it right there. I sub 1 is 1 amp. If I sub 1 is 1 amp, 2 times 1 is 2, plus 1 is 3, 3 over 6 is 0.5. Nobody asked us. That's 0.5 amps. What's I3? I3 is I1 plus I2. We know a couple other things, guys. That's of I guess you could say of some significance. And that is this. It looks like we made a pretty good guess. Absolutely. Nobody asked us the other two. You know what? When we set up to solve the problem, our guess regarding what direction everybody's moving, our guess regarding the direction that these things are moving in, yeah, we guessed right. Why did we guess right? We're getting positive answers for everything. If we don't get positive answers, we guess wrong, we got to take it in another direction. But it looks pretty good. Neat stuff. Good stuff, guys. It's good to know this stuff. It's good to know it. If you know it, I can tell you there are a lot of people who don't know it, haven't done this stuff, or if they've done it, they can forget it sometimes. It's good to have this in your back pocket, be able to know something like this. It puts you in a good position to do a lot of things in physics and in engineering. So that's number 57. 58 is saying this. In a circuit, a current of 1.10 amps is drawn from a battery. So problem number 58. For problem number 58, in a circuit, a current of 1.10 amps is drawn from a battery. Sounds good to me. The current then divides and passes through 2 resistors that are in parallel. One of the resistors has a value of 66 ohms, and the current through it is 0.48 amps. What is the value of the other resistor? This is a great problem. Not particularly difficult, but again, it challenges our understanding a little bit. It challenges our understanding a little bit, and it's just a very nice problem. So let's look at it. It's a bit of an aptitude problem a little bit when we look at this stuff, and it should go pretty smoothly. Okay. For number 58, in a circuit, a current of 1.10 amps is drawn from a battery. The current then divides and passes through two resistors in parallel. We'll assume that's the only thing going on here. There's nothing in series beyond what nothing really in series. Everything's in parallel, and let's make the move here. The current then divides and passes through two resistors in parallel. One of the resistors has a value of 66 ohms, and the current through it is 0.48 amps. What is the value of the other resistor? A number of ways to go here, I guess you could say. They are telling us from the get-go, guys, that 1.1 amps is the situation here. So we can say that 1.1 is the sum of going through one resistor and is the sum of the two currents going through the resistors. So it's looking something like this. In other words, you can call it I. I is, so. All right, we don't need to beat this up. We already know that. We've been down this path before, guys. We know this is what's going on. Either way we look at it. So we've got this. So we got that. They are telling us the one associated with I2, we'll say, the one associated with I2, and whatever that may happen to be, the one associated with I2 is 66 ohms, and they did tell us what's associated with it, obviously. That's I2. That's 0.48 amps. Okay, so these go together. We don't know what R1 is. Don't know what R1 is. We do know that I1 is going to be the total minus what's going through R2. I1 is going to be the total, 1.1, minus this amount of current, and that is, when you do this, 0.52, 0.5, let me see here. Let's just make sure we're on the mark here, guys. Yeah, 0.52, 0.62. 0.62 amps. Yeah, they got to add up to 1.1. So this is I1. This is I2. Yeah, they're going to add up to 1.1. We already kind of know that, so we're there. They both are dealing with. They're both dealing with equal potential because they're in parallel. What does that mean? That means there's a potential difference V. I1 R1 is equal to I2 R2. Is what it means. If these are equal, you can set these equal to each other. I1 R1 equals I2 R2. Sounds good to me. Divide by I2 on each side. And divide by R1 on each side. That's the key to the whole thing, right here. This solves it. You get down to here, you just do the mathematics correctly, and you're on the money. You're fine. I1 is 0.62. I2 is 0.48. I1 is 0.62. I1 is 0.62. I2 is 0.48. R2 is 66. R1 is about to be solved. That's it. That's the mathematics, you guys. Multiply by R1 on each side. Multiply by R1 on each side, then multiply by the reciprocal of this on each side. To make a long story short, you're looking at, it makes sense that what's going through R1 is a bigger answer. So the resistor's got to be smaller. if this is what's going through R1, 0.62, and this is what's going through R2, R2's got this going through it, R2's got that going through it, R1's got this going through it. If there's more current going through it, it's going to be a smaller resistor. It's going to be smaller than 66. We're already checking ourselves to make sure we don't do something careless. For me to get a bigger flow of current, there's got to be a smaller amount of resistance. It's got to be smaller than what they gave me, the 66. And this is indicative of that. When you do this, yeah, you're getting 51.1. That is it. It's believable. Let's see what they got. They got B, letter B, which is 51.1 ohms. We're on the money, guys. We're doing good. That's B. Neat problem, not particularly difficult, but again, all these problems at some level are going to force you to really think it out. What do I know? Even if it's simple, you'd be amazed how many quote-unquote simple problems can be hard to solve. Okay? So just know what you're doing. Get this under control. Be well with this stuff. All right. That was 56, 57, 58. Let's go to 59, 60, 61, which come from one system here. I am going to briefly pause this. Well, you'll not even notice it. I've got a great person doing the editing on this. I'm going to put 59, 60, 61 on the board by putting up a particular circuit, and we're going to play the game and figure out what we're doing here. Okay, let me just see really quickly. Yeah, it should go relatively smoothly. So let's take a look at it. So 59, 60, 61 are going to pertain to something, and we'll take it from there. See you guys in an instant. Okay, everyone, let's do 59, 60, 61. Basically, they give us this figure, and then we kind of fill in the blanks. In the actual practice exam itself, as we said, essentially this figure is given to us, and the stuff in blue, the I1, I2, and I3, we fill that in. We take some guesses, and we try to think, okay, well, I am going to make the assumption that the current is going to flow in the manner in which I'm drawing it. Am I right? Am I wrong? I guess I'll find out. When I solve for I1, I2, and I3, I'll see what kind of signs I get for the answers. If there's a sign that's negative, I guess wrong, and I have to reverse the flow of the current. But you work all of it consistently, and at the very end, you make determinations of what guess you made and whether or not it was right or wrong. So they give us all this initially, and then we say, okay, let's talk. There's this thing called an ammeter, and it tells you how much current is flowing through there. For our purposes, for our assumption is, and I have this written down in the solutions that are going to be scrolling for you at the end of each one of the videos, at the end of each one of the 3 films. The ammeter shown in the figure reads 4.4 amps. They told us that. They said that from the get-go. They said the ammeter shown in the figure reads 4.4 amps. No resistance for our purposes in the ammeter. And from there, they tell us some other stuff. R1, the resistor R1, they call them R1, R2, R3. Resistor R1 is 7 ohms. Resistor R2 is 5 ohms. Resistor R3 is 2 ohms. Okay, they told us that too. I wrote it down R1, R2, R3, and we know that R1, R2, R3 are 7, 5, and 2 ohms respectively. R1, R2, R3. So we have that written down there. We know there's no resistance for our purposes in the ammeter, so let's say it's 4.4 amps going through the ammeter. Okay. That's interesting. Let's draw some conclusions and answer the following 3 questions, 59, 60, 61. They're going to ask us a number of things. They're going to say, okay, they already gave us this. They said I1, They said I1 does this. So I1 does this, I2 does that. They gave us that. They didn't really give us I3, but we draw that conclusion. If these two, if I1 and I2 are coming to this point, there's one place for them to go, and that's that way. So I3 right here is the sum of what's coming in, and that's I1 plus I2. So I3 is I1 plus I2, and we said that I3 going through here is 4.4 amps. So I3 is 4.4 amps. I3 equals this. So you write it any way you want. Just, we've been there before, guys. We're looking at the juncture rule. I3 is the sum of I1 and I2. They told us what's going through here, the ammeter. No resistance for us right here at least. And we're saying, well, at the end of the day, it's 4.4 amps going through here. That's going through the R2. R2 is associated with I3. So kind of watch out. I wish the letters and the subscripts would kind of match up. They don't really match up, but that's okay. This is R sub 2, and it's associated with I sub 3. R sub 2 is associated with I sub 3. I sub 3 is 4.4 amps. I sub 3 is the sum of I1 and I2. And that's what we have up here. So we do have a few things to look at. Let's take a look at it. I mean, what we can do. Well, I'll tell you what. Initially, even if we don't look ahead at 59, 60, and 61, it's a good idea to know as much as we possibly can know. One good way to do that is, why don't we know all the currents that are going on? Well, I'll tell you what. There are things we know, there are things we don't know. I'll tell you what. Let's talk about number 1, number 2, number 3. There's 3 unknowns. Let's write it down. Well, we already know what I3 is, so it's not really a mystery, but let's kind of pretend we don't know it. We know that I3 is I1 plus I2. For 2, we're talking about, for equation 2 here, let's talk about what's going on with the R1 and the I1 and everything else going on here. I am making the assumption, see, and here too, this is kind of interest as well. How is this thing going to work? In a lot of ways, you could say if this flows up this way, there's going to be a breakup this way and a breakup that way. Very likely, you know, as it's breaking up, for this to come around here to get to here, this has got to be I2 also. They didn't really talk about it, but let's talk about it. I mean, if this is going to come around, if this is going to go here and branch off, if I got I2 down here, the I2 didn't come from nowhere. The I2 came from right here. Well, this is I1 then. Because together, I1 plus I2 is going to be what's coming in that way as well. Tell you what, we are looking at a situation that can start in a number of places, I guess you could say. Let's start here. From here all the way to here is 10. Then it drops. It's I1, R1. So it's 10 minus I1, R1, comes around, goes here. It's I3, R2. I3 is 4.4, so maybe, you know, maybe start making that change here. Come around here, goes this way. Sounds good to me. Not too bad. I mean, there's not much more to go beyond that. So let's see here. Let me get some of this out of the way, guys. Seems like some stuff are a little closer than I would want them to be, a little too close for my taste. So we got this. Okay, let's see what they're trying to say here, guys. I'll see what I want to say. You got the I1 going this way. Okay, I got 0 to here, that's 10. Then I drop I1, R1. I go around here. Then I drop I3, R2 right here. And let's see what we got. So we got 10 minus I1, R1 minus I3, R2. Be careful with the subscript sometimes, guys. Heck, we can kind of cut to the chase a little bit. I mean, if right off the bat, we can hit I3 to be 4.4. I didn't do it here in the notes, so let me not do it, for now at least. Here we got I3. Now let's go around again here. Let's go here. We got epsilon or E. Then there's a drop, I2, R3. Another drop, I3, R3 on this time, okay. Forgive me, no, it's not. We go this way, that's epsilon, a drop, I2, R3. Come around here, there's another drop, I3, R2. Be careful. That's kind of what I was worried about, but that's okay. I3, R2 comes around here, comes back. They all add up to 0. Conservation of energy going on there. So what do we got? We got E minus I2, R3. So let's see what I did here. Right. Right. Here's E plus E minus I2, R3 minus R3, minus R2, I3, or minus I3, R2. Yeah, these subscripts can get a little on the confusing side. Okay. Look, just about any question we want to answer pertaining to this figure is found right here, folks. Now, I don't know. Let's just play. Let's play it like we've not looked at anything about what's being asked of us. The more we know, the more that we know, the more chance there is that we're going to get this thing right, that we can do it right, the more that we know. I think once you're looking at those 3 equations and 3 unknowns, you put yourself in a position where you can answer a number of questions. So that's very much the case regarding that. So if you look at it, you know, I guess there's an easy way and a hard way to look at a lot of this stuff. So let's go with it. That's kind of the basis. Let's see where we want to go here, guys. Let me manipulate one a little bit more. And you know, we know, as we said, we know that I sub 3 is 4.4. So 4.4, like I said, we could easily have done that from the beginning and maybe saved ourselves a little bit of time. 10, there's a lot that can be said. Let's try to keep the answers within the realm of, let's see what we could say here. We got R sub 1, we got a whole bunch of stuff here. I sub 3, okay, I just don't, for some reason, I'm not completely agreeing with some of what I'm doing here. I tell you what, let's try to make it a little easier. Since I got I sub 1 and I sub 2, let's try to keep everything in terms of I sub 2 and I sub 3. So I tell you what, I'm not even completely agreeing why even, I did something that's right. I almost don't need to do that, but I did. Okay, guys, there's a number of ways you can proceed here regarding the 3 equations and 3 unknowns. Number of ways to proceed. Let me follow what I showed you, though I not necessarily needed to go that way. For number 2, let's go 10 right here. I sub 1, I don't know what it is, but I do know, you know, on the side here, what's I sub 1? I'm still kind of bothered by why I even did what I just did. Didn't have to do that. I could have left I sub 1 as a variable here. Already know what I sub 3 is. It's 4.4. So I could have just stayed like this. Let me stay consistent with what I did here in the sheet so you can see what's going on. But you did not necessarily need to go there. I'll tell you what I'm going to do. Is it true that I sub 1 is 4.4 minus I sub 2? I sub 1 is 4.4 minus I sub 2. I don't think I even needed to go there, but okay, it's a true story. It's a true statement. Let's write it down then. 10 is 10. R1 is 7 ohms. I sub 1 is 4.4 minus I sub 2. That's true. I don't know that that was the best decision in the world on my part, but it's a true decision. So it's a valid decision, so it works. I sub 3 is 4.4, and R sub 2 is 5. I sub 3 is 4.4. R sub 2 is 5. Okay, whatever. Equals 0. Okay, sounds good to me. Number 3, because they could potentially ask us a lot of questions here. Now this is of great interest in a sense, because I could kind of come back and say, well, okay, you know, I don't know, you want to get technical here. We can make it 4 equations and 4 unknowns. I sub 3 is 4 point, I sub 3 equals 4.4. There's 4 equations here, and there's 3 unknown, whatever. This, let's not lose a lot of sleep on this. They gave us I sub 3. We don't know E, we don't know I1, and we don't know I2. There are 3 unknowns here. It looks like there's 4 unknowns, but I sub 3 is already given to us. So put in the value of I sub 3 right here, and then you got I1, I2, and E that are not known, and you've got 3 equations for it. The unknowns are I1, I2, and E. So it's a little somewhat deceptive here. If you look at it, it looks like there's 4 unknowns here. You'd need 4 equations. Well, here's the 4th equation. I3 happens to equal, you know, I'm not going to write it down, guys, but I sub 3 equals 4.4 amps. So you'd have 4 equations, and you have 4 unknowns. The I3, which is given to you, which is 4.4, the I1, the I2, and the E. You need 4 equations. Well, you already know what I3 is, and that's valid. So you can work it down to this level, 3 equations and 3 unknowns. The other one is saying, this is E. What is R3? R3 is 2 amps. Now remember, there's R1s, R2s, R3s. Yeah, they already gave us those too. Heck, if you want to get technical, there's 7 unknowns there. There's R1, R2, R3. There's R1, R2, R3, I1, I2, I3, and E. Well, here are 3 of those 7 equations. Here's another 3 of them. You can put this guy in there. Forgive me. You can put this guy in there for 7 of them. How much you want to nitpick on this? We know a lot. We can fill in R1, R2, R3, and we can also fill in what I3 is. We got R1, R2, R3, and we got R3 given to us. We got I3 given to us, and R's 1, 2, and 3 are given to us. So those 3 equations are valid. Forgive the overemphasis on this, guys. We don't need to read too much into it. Let's just get it right. R sub 3 is 2, and I sub 2. So R sub 3 is 2, and I sub 2 is I sub 2. Maybe that's the reason we want to go there. It's a lot easier to look at these. And we got guys. We can see what we have to say here. We know that I sub 3 is 4.4, R sub 3 is 5, and you know, right. So let's see here. R sub 3 was 2, R sub 2 was 5, so it's 5 times 4.4, or 4.4 times 5. All right. This stuff is basically easier done than said when you're sitting down doing it, pencil and paper. Just watch what the heck you're doing. Just watch what the heck you're doing. So a lot can be said here. If you want to, you know, we can pull off a lot of stuff here to try to make it all work. And let's see if we can answer everything that we got to answer. We're going to go for I1, I2, I3, and we're going to get E. Well, okay, this one's maybe the easiest one there. Just read the problem and we got that. Got to find that, got to find that, and got to find that. Well, let's see. That's the challenge, the very neat challenge that we're going to be experiencing. So here we are. See where we can go with it. I'm going to take this second one right here, guys, and do some manipulation of it. We can do a lot. Just I guess just we got to be a little bit careful here. Minus all this is plus the opposite. Minus this is plus the opposite. Minus this is plus the opposite. I don't know what we need to do that, but let's go. Let's work with 2, and let's take it. I'll go here, and let's see if we can get this thing to go for us. I got 10 right here. This times this. Right. Let me think here. Let's see what we got here, guys. This is 10. This is 10. Negative times this positive is going to be negative 30.8. Negative times a negative. This times this is negative 22. Well, let's go here, guys. Let's see if this thing is if they're going to let us play the game here, okay. Let's add negative 22 and negative 30.8. Negative 22 and negative 30.8 is negative 52.8, plus a positive 10 is negative 42.8. Seven I2, add a positive 42.8 on each side. It's going to be 6.1 something when we're doing this. Divide by 7 on each side, and I'm getting 6.114 amps for I sub 2. Divide by 7 on each side, 6.114. Okay, well, I'm getting that answer. Let's keep going. If I got 6.114, let me find I1. Yeah, well, here we are. I1 is 4.4 minus 6.114. Wait a minute. Well, okay. I guessed wrong on one of these then. That's all right. You got to stay with it though. At the end you draw the conclusions. Right now, once you're in this particular dance, you've got to go through with it. Okay? Let's just deal with it. This is 4.4. This is 4.4. The answer is 6, and I2 is 6.114. This is 4.4. 4.4 minus 6.114, that's negative, that's like negative 1.714. Okay, that's important. The magnitude is right. The direction I guessed was wrong. That's all right. We'll fix it. Go to E. Well, it's a good question. Go to E. You've got to stay with the answers that you've gotten. I want to make this abundantly clear to everyone. I know I got an answer that means I guessed wrong, but the magnitude of that answer is correct. The magnitude of that answer is correct. If you were to change, the magnitude of the answer is correct. If you want to change it to the right direction, you got to go all the way back and change it to the right direction, and you can make this work out. For our purposes right now, I'm advising staying with the equations that you have. The equations would change. Would they change by a lot? Depends what you mean by a lot. They would change. You'd essentially be getting the right answers, and they'd be the right signs. They wouldn't change drastically, but they would change. Signs would change. We don't have to go there. If we got more time, at some point, those of you who are in my class, we can talk about that. It's kind of an interesting conclusion how this works out. How we're solving these equations simultaneously. Are we using the determinant method to do so? Kramer's rule. Fascinating rule. Fascinating rule, fascinating proof on all that. And we would get, we'd get the appropriate answers. This is not an inappropriate answer. It's just communicating to us that we got to look at it differently. How you would do this to make it work out, you'd have to say, okay, if you're guessing, I don't want to go there. I just said I wasn't going to go there, and now I'm about to go there. Here's I1, you guys. What they gave to us wasn't right. but that's okay. If you switch it this way, it'll work out. But the way it's going to work out is it's going to go here, you're going to lose here, here you're going to lose again. And then, you're going to come around and see how you're going to play it. Here there's going to be a gain. It's going to be a very interesting conclusion how it works out. I mean, basically what you're saying, if you were guessing this differently, that's all well and good. What you're talking about is see exactly what I want to say on this, how we would kind of look at it. The way this would come around, you'd go this way, it'd come this way. Yeah, the way the conclusions play out, you'd be talking about this and this. You would subtract and then get what this is. The equations would look very, very similar to what we already have, but there would be changes in signs. So if you did Cramer's rule, you'd get answers that look identical in terms of absolute values, but the signs would be different. And if we corrected this, the signs would all be positive, actually, through Cramer's rule. Here they're not all positive, but the magnitudes are the same in either application of Cramer's rule in either guess. Regardless of the guess, you're going to get values that have absolute values that are correct. Signs could have negatives and positives in there. If you want to make them all positive, the equations would be changed, and Cramer's rule would get you the correct answer in terms of everything, absolute values, and in terms of the signs that you want to have, all positive signs. It's a matter of just of signs being changed. The structure of the equations don't look a whole lot different. You just put negatives. It's a question of where you're going to put certain signs of how you're evaluating certain things. Absolute values of final answers are going to be the same regardless of which equations you use in your application of Cramer's rule. Pretty fascinating stuff. For our purposes, just let it go. We got what we got, let's go there. We've got this thing looking like this. We've got E looking like, let me add I2, I3 on each side. Let me add I3, R2 on each side. Let's go for it. I2 is 6.114. I2 is 6.114 times 2. That's 12.228. 12.228 right here. I3, they already told us, is 4.4 times R2 is 5. 4.4 times 5 is 22. 22 and 12.228. 22 and 12.228 is 34.228. Everything came out okay. The I1 was, but you have to work with what, if it happened, it happened. 34.23 volts, they go for. That's where the 34.23 volts comes out to. So what are they talking about here, guys? What is I1? Well, okay. You got to be careful here. You got to be careful. You take what they give you. If they ask you, this is just the way to take a test, guys. If they give you options, you work with the options that they gave you. If they don't give you what the actual current is, and in this case, let me just look at it. Yeah, they didn't. Okay, well, then we'll play their game. If they give you options, the reality of this thing is, we already talked about it, the equations and using the beautiful theorem associated with Cramer's rule and all those beautiful equations and the beautiful process of Cramer's rule, you're getting all the right answers. And if the signs are off, we just, at the end of it, we just play games with the signs and put them back to where they got to go. In this case, The answer here should be 1.7 going in that direction. Because they're saying it's going in this direction, it's got to be a negative 1.7. They're the ones who drew it, so let's play their game. They're saying for this one, what is I1? They're saying it's A, which is negative 1.7. That's this guy. So let me... Okay, they want to play it like that. They said 1.7. They said negative 1.7 is what they said. And that's for 59. That's for 59. Fine. If you're going to keep that direction, you do have to call it negative 1.7. If you change that direction, you have to call it positive 1.7. There's a lot you have to do. Again, Cramer's rule is amazing. Beautiful. Beautiful mathematics. The proof of it is fascinating. It works if you manipulate the equations in particular ways. You're going to get different answers, but if you don't manipulate them too much and keep everything where it should be, and you just multiply in a row or a column by negative 1, let's say, you're going to change the answer. Potentially. You may not. I mean, in some instances, you won't. You'll get the same answer if you do it, depending upon what the master determinant is on some of these. There's a lot here, guys. It lends itself better. You'd be amazed how you're getting the right answer no matter how you go about doing it, as long as you've mathematically formulated things correctly. You've set up the mathematics. You've set up the independent equations in n number of independent equations in n unknowns. If you've done that, you're going to get the right answer. The signs might be off on occasion, but we can fix that. The absolute values are going to be spot on, which is really just, I can't emphasize enough how fascinating that is. For number 59, what is I sub 1? I'm going to leave I sub 1 where it is. If it is, then indeed it's negative 1.7, which means in reality it should go the other way. But they're not asking us that. They gave us negative 1.7 amps, no other options, so we got to stay with that. What is I sub 2? For what is I sub 2? I sub 2 is 6.114 amps. They got 6.1 amps. That's good enough for me. 6.1 amps for 60. Like I said, 59 was A. Right. Is that correct? Yeah, right. 59, we said it was negative 1.7 amps. 60, they said it's C. That's 6.1. Well, yeah, 6.114 amps is close enough for me, you guys. And that's where they're going there. And that's no problem. And that's I2. It tends to go in the right direction. What does that mean? I think the fact that it's a big number, this is kind of interesting. You don't have to do this to solve the problem, but I want you guys at least, let's know this stuff. So when you go in there, you can't get fooled. If this is 6.114 amps, this is 6.114 amps, about 6.1 amps. And that one's going this way, that one's going that way. If you're going in here with a real big number, and it breaks off this way and then that way, the two breakoffs add up to 6.114. This right here is 1.7 if you go positive. This right here, let's call it 6.1, right? This is 1.7 going that way. We switch it. So the big amount, 6.1, comes up here. This is 6.1 up here, 6.1. This is 1.7, that's 4.4. Wait a minute. What's 4.4 plus 1.7? It is 6.1. It would be I2. It would be I2 equals I1 plus I3. I2, the big one, would have the I1 going that way plus the I3 going this way. If this was switched over. This is not valid now. It's not valid now, but it would be if you had this thing going that way. Just extra stuff to look at. Again, what is I2? It's 6.1 amps. Okay, we got that one right. That's I2. 61, what is E? 34 volts. You got it. 34 volts, that's A. I mean, this is not the big thing here, guys. I mean, anybody can label. They change the labels on the answers. Do we know how to do this? Can we do this right? You know. Pretty fascinating stuff. With Kramer's rule, if everything in a column changes sign, pretty interesting. If everything in a row changes sign. If everything in a number of columns change sign, and only sign is changed here, or everything in a number of rows change sign, and nothing other than that, you get some fascinating conclusions. Conclusions are all the absolute values of all the answers are the same. If you're going to get an absolute value at the end of everything, they're the same as the absolute values of everything else. If there's consistency with how Kramer's rule is applied. If rows are changed by multiplying by -1 all the way across a row, or multiplying by -1 across a number of rows, not going to be a problem. Things are going to be off by a sign at most. That's it. Absolute values are going to be identical. Fascinating, fascinating stuff that goes on with the mathematics. That was 61. Let's look at 66, you guys, and then we're done. So let's. '66, pretty straightforward stuff to knock it out. Let's get it done. Okay, guys, this one should be a little more, I don't know, somewhat more straightforward or easier to look at. Problem number 66. Problem number 66. Determine the RMS voltage, the root mean square voltage for the circuit. Determine the RMS voltage for the circuit. Determine the RMS voltage for the circuit. So they're giving us a situation here. Pretty easy. The hardest part of this is maybe even drawing it, and that's the longest part of doing it. But you got something like this, and you've got our friend the sine wave here. This is V is 140 sine 500t. Usually they're dealing with radians when they're dealing with something like this. Radians are kind of, those of you who had me as a teacher know that the radians are kind of the lingua franca. It's the language that is frequently used when you're dealing with angles. Here it is. One day I'll learn how to draw a sine wave. That's a sine wave. This right here is 1,000 kiloohms. This one here is 1 Henry. And this right here that's 1 microfarad. This is 1 Henry. Let's see here. Yeah. 1 Henry, 1 microfarad, 1,000 ohms, or 1 kiloohm. We've got this right here. That's definitely associated with that, right? So we got all this. Determine the RMS voltage for the circuit. Not too bad. let me see. There's a lot of ways to go here. They give us a lot of stuff, and oftentimes they're going to try to throw you off. And you could throw you off pretty easily on this one. Tell you what I'm going to do. This is a lot easier done than said. Let's go to here. V is 140 sine V max. Well, if it's oscillating according to a sine function, the maximum value is the amplitude, and the amplitude is 140. That implies, based on the mathematics that we've done in class, that the root mean square of this will be the average of the square of the sine function. The average of the square of the sine function is 1 over the square root of 2. It's the average of the square of the sine function times 140. The average of the square of the sine function times 140 is 1 over the square root of 2 times 140. 1 over the square root of 2 times 140. 1 over the square root of 2 is the average of, it's the average of the square root. Now, let's see this. The average of the sine function, the average of the square of the average of the square of the sine function, square rooted, is 1 over the square root of 2. Easy for me to say. 1 over the square root of 2 times 140 will give you 99 volts RMS, and that is the RMS. VRMS equals 99 volts. And that'll be it. Okay, guys, thank you. Let me just make sure I don't want to leave you here with, this is what I chose to do. It took long enough, folks. It always takes a little bit longer to try to explain this stuff. Other people could probably be a lot more efficient than I am. I don't think there's ever an easy way to look at this stuff if you're going to do it more or less in person or more or less on film. It's easier to look at it as a PDF. You can go at your own speed. When you're doing these problems on an exam, the only person to whom you have to explain anything is to yourself. And you don't have to deliver a speech, and you don't have to run entire, you don't have to run across, entire rooms. You're not erasing everything. You're not delivering a speech to anybody. The only person to whom you're kind of delivering that speech is like a mental note as to what it is that you're doing when you're doing these problems. You're doing it pencil and paper. It should go much faster than what I'm doing. I'm trying to explain this stuff. That's my job. So certainly not a great effort to do that. Many other people, teachers and other people alike, go through much more and do much better. But this is the best that I can do for this. I hope that it works out for you folks. And again, there's just some great resources out there to be consulted. The only way I was able to do any of this stuff, if there's anything decent about it, is I was able to look at some great resources that some other people had done. Otherwise, this is not something that could easily be done, if I could even do it. So I hope it works out for you guys. Good luck to you. Take care.